Let's go through an example of a independent groups or between groups t-test. And we're going to walk through both what it would look like, how we'd analyze it in SPSS, where we'd get the numbers to report, and how we'd report it. So Dr. X wants to study the effects of massed versus spaced study on exam performance. He randomly assigns 20 students to group 1 spaced exam studies during 2 3-hour blocks with 10 people, or group 2 mass studies during 1 6-hour session, again 10 students. So randomly assigning 10 students to the spaced condition and 10 students to the massed condition. He's then going to enter his results. And basically what we have is a couple of things here. We have participant number, so which participant is, and again, there's a total of 20 participants. We have the actual study type, so this is our independent variable, with spaced being coded as 1 and massed study being coded as 2. Now again, this is arbitrary. We could have coded massed as 1 and spaced as 2. But generally speaking, again, when you have a directional hypothesis, you want to think about what you're expecting. As we're expecting group 1 to be larger than group 2, we're expecting better performance with spaced based on previous research and our lit review. We're going to code it that way. And that's usually what's going to determine how we code our independent variable groups based on our expectation, with our first group being usually the group we're expecting to perform better. And finally, we have our actual outcome variable, our percentage correct on the test. So we've got all three things. We've got our participant numbers, 20 of them. We've got our study type, 10 in spaced ones and 10 in massed 2, and we have their actual scores. From this, we're now going to run our t-test analysis in SPSS. So in SPSS, we're going to go to Analyze, Compare Means, Independent Samples t-test. And as I already probably pointed out, there is multiple ways to describe a between subjects or independent subjects t-test. They're all basically the same concept, and if you think about it, they're saying the same thing, just using different wording. So again, in SPSS, it's going to be called the Independent Samples t-test for the between subjects design. We're then going to basically take our dependent variable. We're going to click it on the left-hand side, hit that arrow to bring it over to test variable, and then we're going to take our independent variable and put it in our grouping variable, and we're going to bring that over. So again, the test variable is going to be our outcome, our DV, and the grouping variable is going to be our IV, or independent variable, study type. And with study type, we're probably going to also have to define it. What is group 1 and what is group 2? So again, in this case, spaced is 1, massed is 2. We just let SPSS know that. So then we're going to run the test. We're going to hit OK, and we're going to get the following information. We're first going to get just some descriptive statistics. So we're going to get study type 1 and 2, the number of people in each of those, 10 and 10, and we're going to get the mean. In study type 1, we have a mean of 87, and in study type 2, we have a mean of 67.5, and we're also going to get the standard deviations. 7.52, 7.166 approximately. And then we're going to get the actual statistical test. Now again, the statistical test is going to give us 2 lines. The first thing it's going to give us is Levene's test for quality of variance. So it's going to give us an F and a significance. Remember, this test we want to see non-significant. We want to see it above 0.05. And in this case, that's what we find. Significance of 0.791. So there's not a great difference. What this means is that we can actually use the top line for the rest of our analysis. If the Levene's test was significant, 0.05 or lower, we would use the adjusted bottom line. And notice they're labeled equal variance is assumed and equal variance not assumed. So anyway, based on this information, we're going to use that top line. So we've got our N, we've got our means, we've got our standard deviation. So we have our descriptive statistics for both groups. We have our Levene's test, which is non-significant, which means we're going to use the top line. And then that top line has the information we want to report. We have our actual calculated T, 5.932. We have our degrees of freedom. So remember, there's 20 total participants. Degrees of freedom for the t-test is n minus 2 when it's a between subjects test, so 18. And we have its significance, 0.000 in this case, which we report as less than 0.001. Again, I want to strongly remind you, we never report a p of 0. That would mean there is 0 chance of us being wrong. There's always a chance of being wrong. Just in this case, it's very unlikely. It's less than 0.001. If the Levene's test was significant, so in other words, 0.05 or lower, we'd actually report this bottom line. Notice there's almost no change in this case. The degrees of freedom are slightly less, 79.56 or 96, and it's still significant. The larger the group and the bigger the difference in the Levene's test, the more this value may change. Because what it does is actually adjust the degrees of freedom to a smaller level. Remember, smaller degrees of freedom, higher bar for us to claim significance. So it's making an adjustment for the fact that the equal variances are not assumed. In this case, they were pretty much equal variance, so we're not seeing a very large difference. And we're not going to report this in this particular case. The only reason we'd ever look at this bottom line is if the Levene's test was significant. So generally, when we're reporting this, we'll simply say Levene's test was insignificant, therefore equality of variance was assumed, and here's the results. If it was significant, we'd actually report it. Levene's test was significant, we'd report the F, we'd report the significance, and therefore we use the equal variance not assumed, and here's the results. So as I said, when we're dealing with violations of normalcy, it means there's an unequal set of variance. So unlike the top example of two normal distributions, there's something different in the distributions. In other words, it's letting us know the means themselves are not completely telling us the entire story. There was also a difference in how the groups performed, not just based on their mean difference, but also their actual performance within it. It's generally an indication of a smaller sample size and potentially some extreme or outlier scores. If we do have unequal variance, we adjust the degrees of freedom downward, which decreases our chance of rejecting the null hypothesis, a less powerful test, but it reduces the bias in the pooled variance due to that heterogeneity of variance. That's what it's doing, and it allows us to still look at this test. And sometimes we may find that the top of the equation would have been significant, but unfortunately we violated that assumption, and when we look at the bottom, it actually is insignificant. So that tells us we probably want to look more. Sometimes it actually will still be significant and we can still report it. We just need to let people know that the equality of variance was violated. So just taking a quick look, therefore, we have the independent groups t-test, we've got our means, we've got our standard deviations. We do need to hand calculate the effect size of our t-test if we have a significant effect. And in this case, the t-test has Cohen's d. And here's the equation for Cohen's d. We're basically taking the mean of group 1 minus the mean of group 2 divided by the square root of the standard deviation of group 2 divided by 2 squared plus the standard deviation of group 2 squared divided by 2. So if we actually plug and chug those equations, we can get all that information from right here in the descriptive statistics. So we're going to replace our means with the means of the group, 87 minus 67.5. We're going to replace the standard deviations with, again, 7.53 squared and 7.17 squared divided by 2. If we do that equation, what we get is the top of the equation is 19.5, and the bottom of the equation, again, we're taking the square of 7.53 divided by 2, adding it to the square of 7.17 divided by 2, and then we're taking that value and taking the square root. That turns out to be 7.35. So 9.5 divided by 7.35 is 2.65. That is our effect size of this difference. Our Cohen's d is 2.65. The general rule of thumb of Cohen's d is 0.2 is small, 0.5 is moderate, and a 0.8 or more is large. And indeed, this is well above 0.8. It's 2.65. And there is a large difference. Basically, if you look at the mean on the test, we go from a D to a high B. There's a pretty large shift. We're changing almost 20 points on a 100-point scale. That's a pretty big difference that we're finding with this study technique. So how would we actually or how would we report this? This is how we would report it. An independent samples t-test was conducted. So we basically tell them that not only was it a t-test, it was an independent or between subjects design, was conducted to examine the study time on exam performance, IV and DV. Type of study has a statistically significant large effect on exam performance. T, degrees of freedom 18, the actual value of T, 5.93, the fact that the P is less than 0.001, and the Cohen's d of 2.65. If this was insignificant, we would not report effect size. On average, so again, we're now putting this in English, on average, students who studied during 2 3-hour sessions performed better on the test, mean of 87%, than students that studied on one 6-hour session, mean of 67.5. And we might also put in a graph showing the difference between the two groups. So let's just take that apart. This is the exact same information. I just want to make clear what we're actually presenting here. First, we're telling people what the test was and what our variables were. Second, we're actually giving them the test statement. So basically, was it significant, was it not significant, and what are the stats? If significant, we're including the effect size. And then, if significant, we're talking about the nature of the effect. So this is the process that we're going to use pretty much no matter what the inferential statistic testing is. We're always going to tell them what the test was. We're always going to tell them whether it's significant or not. If significant, we're always going to report effect size. And also, if significant, we're always going to walk through what does that difference actually look like? What does it mean?